Okay, I'm going to try and explain how Kepler's law works. Now, Kepler lived before Isaac Newton, so his rule he got from just looking at data, lots of data. But we can use Newton's law of gravitation to explain how his rule came about. And the way we can explain it is by taking two things. We can take the fact that the reason why these planets, in this case, are orbiting the sun is because they're attracted to it gravitationally, and the gravitational force is F equals G, the big mass in the middle, the mass of the planet that's orbiting it, divided by the radius of the circle, or their separation, squared. Okay. And if we accept that they are moving in a circle, then we also know that that gravitational force is also a centripetal force, so we can use F equals mv squared over r. Now these two forces are one and the same thing, so it's possible for us to equate them. So we can say, okay, big G, m over r squared is equal to mv squared divided by r. Now it allows us to do a bit of cancelling. So obviously the m's, the mass of the object in orbit, is the same on both sides, so they can cancel. The radius, or the separation here, is the same, so we can cancel those. And that just leaves us with v squared is equal to big G m over r, which is an awful lot friendlier looking. Now, if we assume that these things are objects are going in circles, then we also know that if you wanted to get an expression for the speed of the object, we can say it's equivalent to 2 pi r, the circumference of the circle, divided by how long it takes to complete one orbit, which is the time period. And in the case of planets, it would be a year. So we can take this expression for v and we can substitute it into our formula. So v squared, so that's the equivalent of this squared here. So it's 2 pi r. So that 2 times 2 is 4. Pi squared r squared, all divided by the time period squared. So I squared everything here because it's v squared, is equal to g m over r. So what I'm going to do now is I'm just going to try and gather things together. So we've got an r down here and an r up here. So we're going to multiply both sides by r to cancel it on this side. And we're going to multiply both sides by t squared, or the period squared, to make it so there's no divisions. So that becomes 4 pi squared r cubed equals g m times the time period squared. So if we look at all we've got on here, we can see that 4 pi squared is just a number, so that is a constant. G and m for every system is also a constant because that's just the gravitation constant. M is the mass of the object at the centre, which is unchanging. So that is also constant. So that just leaves us with r cubed is directly proportional to the time period squared, or time period squared divided by the radius cubed is a constant. So that means whatever object you've got in orbit around one particular body, then if we take the time period, or in this case the year, and square it and divide it by the separation distance from the centre of the system, and we cube it, we're always going to get the same answer.